Good morning or good afternoon, depending on where you are. My name is Professor Duke Orata. We are continuing with our discussions in thermodynamics, and we are looking at the heat transfer in the machine cycle. Machine cycle. So if you just recap quickly, we know that for a machine cycle, you have the cylinder pressure, cylinder volume, C point A, B, C, and D. This you have a diabatic expansion, you have a diabatic compression, and of course you have the input of fluids here, MF, MC. Remember that the MF plus the MC, that C is the one in the clearance volume. And we have the MF, which exists when the outlet valve is open, and then of course we have the MC, this particular system. That was the piston cylinder model. That was the piston cylinder model where we had our piston. Remember our piston, because those are rings, maybe oil or compression rings. Then we have this as our inlet valve, outlet valve. Inlet, you have outlet. We have our spark unit for injection, depending on what kind of IC you're dealing with. Then we have our piston rod. This is rotary motion here. Here is a reciprocating motion. We're just reminding ourselves. Reciprocating motion. Here we have the BDC, that's the bottom dead center, top dead center, that's the engine piston stroke, this is the piston cylinder wall, this is the piston. So please, we know what happens in this particular system, and we have discussed those in our earlier lectures, and we are still going to continue discussing them in our subsequent lectures on internal combustion engines and so forth. Now, for the state points, let us for the state points. First of all, for the state points, a state point A to B, a state point A, state point A, the volume at state point A is delta MC V1, corresponds to that pressure P1, pressure P2. State point B, we have delta MC plus delta MF, P1. At state point C, we have, remember, specific volumes, we have delta MF plus delta MC, V2. And state point D, we have delta MC V2. Now, if we take the overall expression in this system using first law of thermodynamics, we know that du is equals to dq plus dw. du is equals to dq plus dw. So if you integrate over the whole cycle, remember, when we talk of these cyclic integrals, we say they consist of four-line integrals for this particular case. That's for process A to B, B to C, C to D, D to A. I encourage you to look at our discussions on Carnot cycle, where we've discussed extensively these cyclic integrals and the line integrals. Now, so in other words, each cyclic integral here has four line integrals. And we know that du is a state function, so a cyclic integral is basically 0. So we are left with cyclic integral dq plus cyclic integral dw. Now, let us look at those. So that you get expression for heat in this particular system. Now, remember that we are talking about adiabatic expansion and adiabatic compression, and that will base the polytropic equation. In the case where we have the mass transfers in processes A to B, C to D, and so forth, then there we are not talking about that. So that what we have here is the cyclic integral dq. So the cyclic integral dq is minus cyclic integral for dw, and the cyclic integral for dw is pdv. Remember, from is pdv from A to B plus B to C plus C to D plus D to A, pdv. The same is applicable, line integral for heat there. We are going to look at that. Now, we are saying that for the processes, remember the process just in recap V. So we have A, B, C, D, state points. Remember, this involves mass transfer. That involves mass transfer. So of course it is P, pressure. That will be pressure 1. That will be pressure 1. That will be cyclic integral of dq is, we are talking of pressure 1 into VB minus VA. Then we have for B to C, we have to use the polytropic equation, and you know what the polytropic equation tells us in terms of these quantities. The polytropic equation is P2V2 minus P1V1 over 1 minus N. That is from C to B. And then the other one is, again, this mass transfer, W is 0, mass transfer, W is 0, but you are putting them just for completeness. That will be 0 because it's mass transfer. Again, for C to D will involve mass transfer. That is P2 into VD minus VC. Again, that will be 0 because mass transfer, plus P1, P2, V2 minus P1, V1, 1 minus N, 1 minus N, and that is from A, that is from, what are we having here? B to C. So we have A, then we have D. Yeah, D to A. Now, if we put in this quantity, so we are seeing that what we are left with for heat dq is simply P2 V2 minus P1 V1 or 1 minus N, then plus P2 V2 P1 V1 or 1 minus N A D. Now let us solve for this particular expression for heat. Let's solve that particular expression for heat. So what do we have here? What do we have in this particular case? We are what did we put our limits? This limit was CB. This was AD. Now, so we have P2 for C, and for the state point, let's look at it again. For the state points, we say we have MC, delta MC, delta MF, delta mf plus delta mc, delta mf, existing system, delta mc. Let's just work with it. So this particular one, integral dq, yeah, we have P2 for state point. For state point, we have A, B, C, D. For state point C, that would be delta mf plus delta mc into V2 minus, for B is P1 delta mf plus delta mc V1. All these are over 1 minus n, over 1 minus n, then plus, for A here we have, what do we have for A? Where we are going up to point A, we have, for this point A, we have that particular one is the final one, so it should be P1, into delta M C V1, P1 delta MC V1 minus P2, that particular point, P2 where we have our D, that should be delta MF delta MC V2. This is, again, this is over 1 minus n. Just like this one should be over 1 minus n. But you can split them up so that we have, we just sort it out. Let's break them down. 1 minus n. So we have plus that, then minus. Very good. Plus, minus. Very good. So let's simplify now our expression for heat. Simplify our expression for heat. So all one needs is proper bookkeeping of the substances and the thermodynamic variables, and you'll always be home and dry. So the integral of dq. Now, if we open up these quantities, we have P2. Let's have 1 over n, 1 over 1 minus n, and then open up these brackets. So is there anything which is eliminated with the other one? This goes to that. That vanishes. The two vanishes. They're the same, but in opposite signs. And so we have minus. We have basically P1 delta MCV1 over 1 minus n minus P1 the MF plus delta MC V1 1 minus n. I think we need to delete these particular ones. Give us space. We can simplify. We have repeated ourselves. We don't need these quantities there. We have already taken care of that. We factored it out. So we have dq. We have some quantity will vanish here. 1 over 1 minus n into P1 delta MCV1 minus P1 delta MFV1 minus P1 delta MCV1. So what are we left with here? It looks like that one also vanishes that. So you're basically left with the integral for dq is simply given by minus P1 minus delta MF P1 V1 for 1 minus N for this particular system. Now, remember again, we say that even for this particular one, for this particular system, we are talking about 4 line integrals associated with these particular systems. And so for the cyclic process, the overall process involving heat transfer in that whole machine cycle, then the overall heat which is being transferred in this particular system Q is minus delta M FP1 V1 over 1 minus N. If you multiply by the number of machine cycles, then we have, if it's like N as the number of cycles per unit time, then we will have Q as equals to M1 P1 V1 or 1 minus N, where of course you see that N times that mass flow rate is basically what we are calling M1. So that's our expression for the heat process in this machine cycle. We'll continue with other lectures.